All right, what's up, everyone? What's up, Enschfrosch? This is going to be the first video in a series of midterm review videos for your upcoming lineage midterm. Your midterm is on Tuesday this upcoming week, which is March 25th from 6:30 to 8:30. I think you should check your on cue probably for like what room you're actually writing in. Some additional information is I'll be hosting an Englinks workshop, which I think is paid on Sunday. I believe from 6:30 to 8:30, but I'll get confirmation on that time. And additionally, I'm running a free help desk with Englinks Monday night, 6:30 to 9:30 in Beamish Monroe, BMH 313. You can basically just come pull up, ask any questions you have, and I can try to help answer them before your midterm the next day. So this is the first video. I'm hopefully going to go through all of our main concepts that you should know, just like conceptually. The next video is going to go through some calculation examples of past exams, and the third video will be some more proof-based questions. Obviously, this is by Jack from jackswitzer.com. I updated the website with some new info for the midterm, so go check that out. So just diving into things, what we want to know for this is what's a linear transformation and how can we prove something's a linear transformation? We want to know about the image and kernel subspaces and how those both relate to surjectivity and injectivity respectively. That'll also tie into this idea of the rank nullity theorem. So how does the dimension of our domain or our input vector space relate to those image and kernel subspaces? Lastly, we're going to talk about some matrix ideas like the standard matrix, how to do RREF, and parametric forms of equations. And lastly, we'll talk about basis and dimensionality, which is kind of going to tie into the 2, 3, and 4 idea. So just diving right into things, starting off with a linear transformation. A linear transformation is simply a mapping from one vector space V to another vector space W that preserves our regular notion of vector addition and scalar multiplication. Now, what's that actually mean? That means that the transformed version of adding two vectors u and v should simply be equal to the transform of u plus the transform of v. Okay? And this works similarly with scalars. So linear transformations should scale linearly whether you multiply inside, so you multiply c by v inside your transformation, or you can simply bring c out and you should get the exact same value as multiplying simply the transformation of that vector itself. So this is our usual notion of linearity. We simply want to make sure that for a linear transformation, we can split things up evenly under the vector space kind of operations and ensure that we can just take transformations of individual vectors and then add and scale them appropriately. So diving into a little example here, we're going to show that the transformation of xy, which maps to x minus 7y in the first component and 3x plus y in the second component, is linear. Now, there's a mapping from R2 to R2, and a good idea that this will be a linear transformation is that, so for example, in the first component, x minus 7y is simply a linear combination of, our vectors x and y. So for a linear combination, it's probably a pretty good idea that we're going to be a linear transformation. Now, diving into how do we actually show something's a linear transformation, we want to show this kind of golden equation right here. So you can do this step by step, or you can just do this all in one by taking two arbitrary vectors in our input space, as well as two arbitrary real valued scalars. So we want it to be arbitrary because we want to show this holds for everything. Then we simply want to show that the transformation of alpha times x plus beta times y is equal to alpha times the transformation of x plus beta times the transformation of y. Okay, so we're going to do this kind of how we do every single one of these proofs or like scalar property things. We're basically just going to take the transformation of that alpha x plus by, beta y, and we're going to factor some stuff out. So when we take the transformation, we go to something like this. This is simply just following the rules of what we were given. Now, luckily, we can factor this really nicely into these things I nicely highlighted. So alphas are corresponding to that part, and betas can be factored out to get us this part. Now, since this is just a linear combination, we can also move these things linearly and kind of bring out terms. Now, what this is telling us is that our alpha value, if we bring it out, we are essentially left with alpha times some object here and beta times some object here. Now, what are these two objects? Well, they're directly the transformation of what our vectors x and our vectors y are. If we look up here, x minus 7y, 3x plus y, they are the exact same as, a or c minus 7b or d, and then the same thing in the second component, okay? So what we just showed is that this does split linearly. This is exactly equal to what we wanted to show it was. The transformation of alpha times x plus beta times y is just equal to alpha times the transformation of x plus beta times the transformation of y. And therefore, t is a linear transformation. So this is a really useful property. You'll probably be asked to show something like this. I would say this is useful to go over, and we'll do some more examples in the next video. Now diving into our kind of next big group of concepts, we're going to be talking about both the image and the kernel subspaces, how those relate to rank nullity theorem, and how that also relates to the idea of dimensions or bases. So just diving into things, the kernel of a subspace, the kernel of a linear transformation is a subspace, but more importantly, it's the set of all vectors in our domain that map to the zero vector of the codomain, okay? So essentially we're asking, what gets mapped to zero? This is some notion of kind of loss of information, because where we remember, we have this idea of function injectivity, where a function is injective or one-to-one if every input maps to a unique output. Now, if we have the only thing in our kernel being the zero vector, so if the zero vector is the only thing that maps to the zero vector from the domain to the codomain, then we are injective. This is also similar to saying that the dimension of our kernel, of our linear transformation, is equal to zero, because the zero vector has zero dimension. So if that's true, then we are injective. Now, next, going on to the definition of the image. The image is simply everything that gets mapped to. So, you send every single possible input from your domain. Now, what is the total set of things that pop out of your codomain? Okay? Now, this has another similar property where we have surjectivity, where we remember surjectivity is if we map onto the whole codomain, or the whole output space. Now, if our image is equal to the entire codomain, we're surjective, right? So if what we map to is exactly equal to the space itself, we have this idea of surjectivity. Now, I should say quickly, both the kernel and the image are both subspaces of the transformation. Now, what's it to mean to be a subspace? The main thing is we have this closure property, right? So if we take two things in the kernel and we add them together or scale them, we should still be within the kernel because it is a subspace. Now, these tie really nicely into our idea of rank nullity theorem. So rank nullity theorem is essentially something that relates the domain of our input space to these other subspaces we just talked about. So technically speaking, the rank nullity theorem states that for a linear transformation that maps finite dimensional vector spaces, we're going to call them V and W, then our dimension of V, the dimension of our domain, so everything that we can send from our input space, is simply equal to the information we lose, so the dimension of our kernel, as well as the amount of things that we map to, the amount of unique linearly independent things that we map to. Okay? So basically, when we're mapping stuff from when we're mapping stuff from our input space, they can either be sent to zero or they can be sent to some value in the codomain. Okay? Now, we're going to kind of bring this all together after we talk about bases. So a basis is simply a linearly independent spanning or generating set. So it's a set of vectors. They don't have to be unique necessarily. So I hat and j hat are the standard basis for R2, but 2 times I hat and 2 times j hat would still be a basis because they're still linearly independent and they would still span the entire space. Now, you can think of a basis as the minimal amount of information needed to represent the whole output space, or the whole space of your vector space in general. Now, the dimension of our vector space is simply how many things you have in your basis. So we have to be linearly independent and we have to span. You can have multiple bases, but they all must have the same number of vectors, or you wouldn't have your linearly independent properties. So once again, the standard basis of R2 would just be I hat and j hat, or 1, 0, and 0, 1. Now this kind of makes sense because if we pick an arbitrary point in R2, so this guy is in R2, 3, negative 7, we can simply get there by doing 3 times I hat minus 7 times j hat. Okay? So this all kind of ties together with the idea of our linearly independent things. So rank nullity theorem is basically telling us the dimension of our input space, or how many uniquely, like linearly independent spanning objects we have. Do those combinations get sent to 0? Do we lose information? Do we just go to the same exact point? Or do we map to some unique part of our output space? And then, I guess more succinctly up here, we also know that injective is equivalent to being our dimension of our kernel of L, which is our linear transformation, is 0, and surjective is equivalent to simply the image of our linear transformation equaling the codomain, which is the same as having the dimension of our image of L equaling the dimension of our codomain. Because dimension relies on linearly independent things, so that object should be the exact same. Now, diving into my favorite topic, matrices. Most importantly, the standard matrix. So the standard matrix is a way of representing linear transformations using matrices. So if we have a linear transformation mapping from Rn to Rm, it would be the matrix that's n by n, such that for any vector in V, for anything that we input into the space, the linear transformation of the vector would be exactly equal to our matrix representation of the transformation matrix multiplied with that vector itself. Oh, okay. Now, the standard matrix specifically relies on mapping the standard basis of Rn and Rm and seeing how those transform accordingly. Now, just a reminder, the standard basis is essentially where you have a 1 in one position and zeros everywhere else. So in R3, for example, you'd have like 1, 0, 0, but then you'd also have 0, 1, 0, and then you'd finally have 0, 0, 1. So you'd send all these into the vector space, you'd figure out what you get back, and that would kind of tell you what the standard matrix should look like. Now, if we look at this in practice, if we, for example, have this linear transformation called T, which takes in input values of A, B, and C, and maps from R3 to R2, we can set up our standard matrix here by basically pulling out the coefficients. So in this case, when we send in 1, 0, 0, I should say it's more like this. When we send in 1, 0, 0, we get out a 2 and we get out a 4 in the first and second component, which we can think of as like the x and y axis. Now, when we send in 0, 1, 0, we're going to get out a 1 and a negative 3, a 1 and a negative 3. And lastly, we don't have a c in this component and we have a 2 in this component. So we'd get a 0 and a 2 back. Okay, so this is our standard matrix, and it's pretty cool. So we can represent our transformation by simply doing this matrix multiplication right here. Sorry, this should be a 1. So we can do this matrix multiplication and get the exact same answer back. But what's really useful here, and the point of matrices and matrices, is that they're very, very easy to compute, especially for a computer itself. So, how do images or videos get drawn to your screen? Well, it's through matrix multiplication. Or how does ChatGPT get trained? It gets trained by matrix multiplication. Or it gets inferenced by that, at least. So it's really, really important computationally because it can do things very quickly, especially on specific computer hardware. But in the context of this class, it's also very useful to find the notion of dependence. So just because we have a linear transformation doesn't mean everything that we're sending is actually linearly independent. We don't know if we're mapping all of R2, for example. So in this case, we're mapping from R3 to R2. What we want to do is we want to find out what is linearly independent and what isn't. So I guess just a quick refresher, we're going to use something called reduced row echelon form, where essentially we want to isolate leading ones, and every leading one should have zeros above and below it. So leading one, zeros, leading one, zeros, leading one, zeros. And we should also have a couple other things. So if we have that leading one, we shouldn't have anything in front of it. And we also shouldn't have anything above or below it. And we should make this kind of staircase pattern. Additionally, if we have a row of all zeros, that should be sent to the bottom. Similarly, in the example of this equation, for example, we have 2, 3. So we basically have some stuff that's like leading that isn't a 1 or a 0, but it's pretty reduced, okay? So it's almost, but not quite there, essentially. Oh, okay, whatever. So jumping into things, I guess, quickly the importance of this. REF allows us to identify solutions of a system of linear equations, find bases for our basic things like the column, row, and null space, identify how many solutions this system has. Does it have one? Does it have infinite? Does it have none? These can all be told to us by this matrix representation. So diving into how we actually do REF, essentially how we can do REF is we can add and scale row vectors, okay? So we can multiply them by real value numbers, and we can also add and scale the two by like adding rows and adding columns together. And this is all tied back to this being a linear transformation. The rows behave linearly, we can treat them as such. So going under these rules, firstly, we want to get rid of this guy down here, because then we can create a leading 1. So what we're going to do is just take 2 times the first row minus the second row. That's going to give us a leading 1. Now, when we do this, we're going to end up with something that's not a leading 1. Whoops. Something that's not a leading 1 and something that's not a leading 1. Therefore, we can just scale them appropriately and get to what we need. So we just divide the first row by 2, divide by the second row by 5. We got leading 1s, and we're so close to being done, but we still have this pesky guy up here. So what we need to do is simply subtract off half of our second row in order to, fully get rid of that so we can have our REF property. Now, this finally gives us an REF when we're mapping the input space to the output space. We'll have leading 1s, and then some weird things in here. Now, what this means really is both A and B, when they're isolated themselves, they depend solely on this third variable C. We have some notion of dependence there. So looking at this in a parametric form in the next question, what we can do is something like, we want to check what maps to the kernel. So the kernel is simply like this augmented matrix here, where we just add the line, which means an equal sign. So we added an equal sign. We set it equal to 0, 0. Now, these scalars would normally change as we are doing REF, so those would be important to know. But in this case, because we're just mapping to 0, adding and scaling 0 doesn't change those values. So those will still be 0 after our REF. Now, what we find out here is, we have this row that everything seems to depend on. So we're just going to call it T. If we had more of these rows, we'd call them T1, T2, T3. But we can simply write out this matrix as our linear kind of a system of equations. And what that gives us is that A is going to be equal to negative 0.2 times T. B is going to be equal to 0.4 times T. And we can just parametrically answer the equation of what ABC values map to the 0 vector. And we are told that a whole line in our input space, this negative 0.2x, 0.4y, and 1z, any scalar times that will map always to the 0 vector. Now, what this tells us is that the dimension of our kernel is certainly greater than 0, because if we multiply t equals 0, we're going to get the 0 vector mapping to the 0 vector, which is great. But then we also have this whole other class of objects, this whole line within R3 that's going to also map to the 0 vector. Now, using what we knew from before, if the dimension of our kernel is greater than 0, then our transformation itself cannot be injective, right? It can't be 1-to-1, which makes sense. We're mapping R3 to R2. It makes sense we shouldn't have this 1-to-1 correspondence, right? Because going down a dimension from your transformation, you should probably be losing some information that you can't recover. So you couldn't create a bijection, for example. That wouldn't make sense to be able to go down to a smaller space, come back up to the bigger space, and have all the information you originally had, right? Okay, so this is our last video in kind of the content review section. I will see you all in the next one where we're going to start talking about some more calculation examples. Cheers.